This is a short lecture on the Transport Layer Security Protocol uh, for COP 621 Web Security at North Carolina A&T State University. Transport Layer Security provides encryption and privacy and data integrity between two communicating entities. It provides the security in HTTPS. And it can be used in other applications such as email, messaging, voice over IP. Can all use TLS to provide security over the network. A browser using the normal HTTP will connect to a server on port 80. Port 443 is used for HTTPS. A lot of servers will support both HTTP and HTTPS. When a browser connects to port 80, the server may return a 301 move permanently status that tells the browser to, from then on, use HTTPS on port 4043 instead of using port 80. Before TLS was created, we had the Secure Socket Layer, or SSL. That was created at Netscape back in February 95. In January 1999, a Internet Engineering Task Force work group created the TLS protocol. And in June of 2015, the old secure socket layers were deprecated, meaning that no new applications should use it and existing applications should modify over to use TLS. There's really very little difference between the first version of TLS and SSL 3.0. TLS 1.3 is the current version. Don't use nothing earlier. TLS and SSL do not quite fit into the 7-layer OSI model or the 4-layer TCP IP model. TLS runs on top of TCP, uses the services of TCP to have a connection-oriented protocol. And then it, in turn, is used by applications as if it was a transport layer protocol. Just to mess up the division of layers, the applications must be actively involved in the TLS handshake. Now, one of the big reasons we have the TLS protocol is that there's a significant performance difference between symmetric and asymmetric encryption. Symmetric encryption, or private key encryption, which is usually AES, is much faster than asymmetric encryption or public key encryption, which is usually the RSA algorithm. Some measurements show that AES is about 200 times faster than RSA. Also, several CPUs, including the Intel x86 and 64-bit versions, contain hardware to speed up the AES algorithm. Now, when a TCP connection forms, it takes 3 messages back and forth to the server. The first packet is sent from the client to the server, telling the server, I'd like to connect. The server then sends a response called the SYN-ACK that tells the client that the server is ready to do it and confirms some parameters that the server sent about window size and other aspects. And then the client acknowledges that it's got the information from the server. At that point, the connection has been established and the two entities can start communicating. During or right after the connection, TLS starts to set up a secure communications channel. The client sends a request to the server giving options about what hash algorithms and what encryption algorithms it's willing to use. The server then picks its favorite encryption algorithm and hash algorithm and responds back to the client and sends the client the digital certificate of the server. The server then makes a random number that's going to be used for a key, encrypts that random number using the server's RSA key, which was in the digital certificate, and sends it over to the server. So we're sending the encrypted key over to the server. And then now both the client and the server have a common random number, and from that they make a common AES key. At that point, they both have an AES key, and they switch from the RSA algorithm to the AES encryption algorithm, and all the data henceforth is transmitted with AES. Here's a picture showing the handshake that starts the whole thing. We start with a couple messages that are just involved the TCP protocol. The client sends a message to the server saying, I want to connect, and then under TCP it sends a protocol. At that point, when the client responds to acknowledge the server, it also sends information about the request. It says, I want to be using TLS. Here's the protocols I like. The server responds saying, okay, I got those. These are the ones I'm going to use, and they go messages back and forth to share the key. And finally, now they both have a key. At this point, they have a shared AES key, and the client can start sending data to the server and so forth, and on and on and on. Instead of sending random numbers, the client and server can use the DiffieHellman protocol to create a shared keys. Both ways work just fine, unless you got nuclear secrets to send. The server sends its digital certificate to the client, and inside the digital certificate is the common name of the server. The client can then check that this common name is the name of the server that it hopes to connect to. Therefore, it knows that this is the correct server, that this server has a certificate with the name of that server within it, and that it's validated by the certificate authority. The client should also check that the certificate has not been revoked. That is, the certificate hasn't been released to the public and people think that it's invalid. So it should check to see that the certificate is still valid. It is possible with TLS to authenticate the client. In other words, normally with normal web browsing, people who don't always have certificates, the server authenticates so the client knows that it really is the server you want to connect, but the server isn't quite sure who this client is. In some situations, it may be valuable in a business connection to validate the client so that the server knows that the client is really who they say they are. TLS supports many different encryption algorithms and hashing algorithms. If you have a server and you're configuring TLS, you want to set it to use only the most secure algorithms and enforce the browsers to use those secure algorithms. Now, if you have multiple pages you're getting from a server, you want to make sure that you use TLS for all the pages, not just the ones that have sensitive data. For instance, you may have a graphic that you think is pretty clean, it's just a logo or something, but you don't want to just send that in the clear. You want to use TLS because then all requests to the server are encrypted and nobody knows what's going on. Also, with your cookies, you should use the secure cookie flag. Secure tells the system that this cookie can only be sent over an HTTPS or TLS secured connection.